All right, let's dive into a real head-scratcher in the world of AI, non-determinism. It's this technical mystery that has stumped so many researchers. Why is it that an AI can give you two totally different answers to the exact same question? Well, the answer is not at all what you might think.
You've probably seen this happen yourself, right? You ask an AI something, you get a response. Then you ask it the exact same thing again, maybe even just by hitting resubmit, and you get a completely different answer. So what's going on here?
And here's the really weird part. This happens even when you crank the model's temperature setting down to 0. Now, that setting is supposed to kill all creativity, force the AI to be totally deterministic, to always choose the single most likely next word. But even then, the randomness sticks around. And that is the real mystery we're trying to solve. So, where do you even begin to look? Well, for the longest time, the go-to explanation has been what's called the floating point hypothesis. So let's treat that as our prime suspect. This idea is, it's everywhere in the field. The theory goes something like this. GPUs are doing thousands of calculations all at once, in parallel. And because of that, the exact order those calculations finish in can change just a tiny bit every single time you run it. And those tiny, random differences, thanks to some quirks in how computers do math, can snowball into big, noticeable differences in the final answer. The key idea behind this whole theory is something called floating point non-associativity. It sounds super complicated, but the concept is actually pretty simple. You know how in math class, a plus b plus c is always the same as a plus b plus c? Well, on a computer, which has to round things off, that's not always true. The order you do the math in can actually change the result. Okay, check out this example. It makes it crystal clear. Let's say you add a really tiny number, 0.1, to a truly massive number. That tiny 0.1 is so small in comparison that it just gets lost. It's a rounding error. So the computer thinks the answer is just the massive number. Then you subtract that same massive number, and you're left with 0. But watch what happens if you just switch the order of operations. If the computer first subtracts the two giant numbers, they perfectly cancel each other out and you get 0. Then it adds the 0.1. And now you get the right answer. Same numbers, same operations, totally different results just by changing the order.
That seems pretty solid, doesn't it? The random order of calculations on the GPU must be what's causing the randomness in the final answers. So, case closed? Well, not quite.
And here's the plot twist. When some researchers actually put this to the test, they ran a standard super-paralleled matrix multiplication on a GPU 1,000 times. And the results? They were bit for bit identical, every single time. If the theory was right, we should have seen tiny little differences, but there were none. Our prime suspect has an alibi. The mystery continues.
So if it's not the random order of the math, then what on earth is it? Well, the true cause is something a lot more subtle, and honestly, way more fascinating. It's a lack of something called batch invariance.
So here's the real secret. The randomness isn't coming from how your single request is being calculated. It's coming from who else is being calculated right alongside it. Your answer can literally change depending on how many other people's requests are in the same batch as yours at that exact moment. The size of the crowd changes the math. This is so interesting because it creates two completely different realities. From the server's point of view, everything is perfectly deterministic. If you give it the exact same batch of, say, 20 requests, it will spit out the exact same 20 answers every single time. But from your perspective, as a single user, you have no clue if your request is in a batch of 20 or a batch of 200. Those other users are totally random, and that randomness makes your individual result feel random too. And listen, this isn't just a theory. It's been proven with hard data. When they tested it, they found that if you calculate an answer as part of a big batch, you get one result. But if you take that exact same query and calculate it all by itself, you get a numerically different result. The context of the batch literally changes the answer. So now we've unmasked the real culprit. And the best part is this isn't some fundamental law of the universe we just have to live with. It's an engineering problem. And you know what? Engineering problems have solutions. To get this batch invariance, engineers had to get their hands dirty and redesign 3 really critical parts of the AI's architecture. They had to rework the normalization layers, the matrix multiplications, which are the real workhorses, and the attention mechanism itself. For each of these, they had to invent brand new ways of calculating things that would give you the exact same bit-for-bit identical result no matter how big or small the batch was.
So what happens when you actually solve this massive engineering challenge? The payoff? Well, it's pretty incredible.
So the researchers set up a really elegant experiment. They took a powerful language model, set its temperature to 0 to make it as predictable as possible, and then asked it the same question. Tell me about Richard Feynman. And they did this 1,000 times. Okay, so first they ran the test on a standard, off-the-shelf AI model. Remember, 1,000 identical questions that should get one single answer. The model produced, get this, 80 different, unique answers. Then they ran the exact same experiment, but this time using their new, consistent, batch-invariant engineering. The result? 1. A single, identical answer, 1,000 times in a row. They had done it. They achieved perfect, predictable, deterministic consistency.
Okay, that is a seriously cool technical achievement, no doubt. But, so what? Why does this actually matter for anyone outside of a computer science lab?
Well, it matters a lot. For scientists, it means you can finally have true reproducibility in AI research, which is a huge deal. For actually training AIs, it unlocks a much more stable and efficient training method. And for the real world, it means we can finally start building critical applications, things in medicine or finance, that depend on AI being reliable and predictable every single time. This chart really shows you what a game changer this is for training AIs. That tall bar on the left, that's what happens now. The learning process gets unstable and just falls apart. The middle bar shows the typical workarounds, which help but aren't perfect. But look at that bar on the right. That's the result of this new deterministic engineering. The divergence is 0. It's a perfect, stable learning process. That's a massive leap forward.
So what's the big takeaway from all of this? It's really about a fundamental shift in how we think about this stuff.
This randomness we see in AI models, it's not some magical, unavoidable property we just have to accept. It was a really subtle, really tricky, but in the end, a solvable engineering problem. And that leaves us with this really provocative final thought. If this so-called randomness can be engineered away, what other things that we think of as fundamental limits of AI are actually just the next set of engineering problems, just waiting for someone to solve them?